Welcome to the deep dive. Today we are diving into the fascinating world of constructive mathematics. And I think this is going to be particularly interesting for you, as our resident philosopher. I mean, you've already given a lot of thought to the nature of truth and existence. But constructive mathematics takes these questions and it applies them to the very foundations of math. So, we're going to be primarily using the Stanford Encyclopedia of Philosophy entry on constructive mathematics today as our guide. And it asks us to imagine a world where mathematical proof, it's not just about theoretical possibility. It's about actually like a blueprint, a recipe for constructing the objects in question.
Yeah, I think what's so interesting about constructive mathematics is that it really challenges the traditional or, the classical view of math that a lot of people are sort of used to, especially when it comes to this idea of there exists. In classical math, saying something like P or Q, it just means that they can't both be false. But in constructive mathematics, we need more than just the possibility. We actually need to have a concrete method or an algorithm to demonstrate that, to actually show that the thing we're talking about exists.
So let's make this concrete. Maybe a classic example. So the Goldbach conjecture, which states that every even number greater than 2 is the sum of two prime numbers. Classically, we'd say, okay, it's either true or false. But how does constructive mathematics approach something like that?
So constructively, we wouldn't be satisfied with just a true-false. We would demand that you give us an algorithm or set of instructions that we could follow to find those two primes for any even number you give me.
So it really is about moving from this abstract possibility to tangible constructibility. And that has huge implications, especially when we start talking about things like infinity and the continuum, which classical mathematics often deals with in a very abstract way.
Absolutely. Classical mathematics often relies on sort of non-constructive arguments, especially in those areas, relying on reasoning that doesn't necessarily give you a concrete way to construct those objects, whereas constructive math is really asking for that. It wants that recipe.
Okay, so let's get into the heart of how constructive logic actually works. And this revolves around something called the BHK interpretation, which is named after Brouwer, Hating, and Kolmogorov.
Right. So the BHK interpretation reframes each logical connective as an instruction for building a proof. So and, or, implies, not. These all become steps in this recipe for constructing a demonstration.
Now, I think some people might have the idea that constructive mathematics is really just about avoiding proof by contradiction. But that's not quite the full story, is it?
Not at all. Proof by contradiction is perfectly acceptable in constructive math when you're proving a negative statement. So, for example, the classic proof that the square root of 2 is irrational. That proceeds by assuming that it is rational and then arriving at a contradiction. That proof is perfectly constructively valid. The key difference is really in the kind of proof that's required for positive existential claims. So you need an algorithm to produce the object.
So it's not so much about banning certain proof techniques. It's really about a shift in focus towards the kind of proof that you have to offer, especially for these positive existential claims. It's not enough to just say it must exist somewhere out there. You need to show me how to build it.
Right. It's about providing that blueprint rather than just waving your hands and saying, trust me, it's out there.
Exactly.
And so that actually leads to some different varieties of constructive mathematics itself.
Yeah, we have these different schools of thought, like intuitionistic mathematics, or INT, which is really rooted in Brouwer's idea of mathematics as a mental construction.
And that leads to the acceptance of some really powerful principles like continuous choice, which can be very counterintuitive from a classical perspective.
And then there's recursive constructive mathematics, or USS, where everything is defined in terms of computable functions, which has a very computer science-y feel to it,
Yeah,
with its focus on algorithms.
absolutely.
And then, of course, we have Bishop's constructive mathematics, BHES, which is maybe a more pragmatic approach that focuses on working with intuitionistic logic, but it doesn't actually commit to any specific computational model. And this is where a lot of the practical work in constructive analysis has been done. And then finally, we have Martin Lust's type theory, ML, which is really a fascinating system where propositions themselves become types, and proofs are objects of those types. And this is a system that really excels at formalizing constructive mathematics in a way that makes it easy to extract computer programs from proofs, which is pretty amazing.
Yeah, and I think for you, as a philosopher, the philosophical underpinning of these different branches of constructive mathematics would be very interesting to explore. Because each of them offers a slightly different perspective on the relationship between mathematics and computation and, the nature of truth itself.
And speaking of foundations, we can't avoid talking about the axiom of choice, which allows you to make potentially an infinite number of choices without specifying how you're going to make them, which feels very non-constructive.
Yeah, I mean, you're absolutely right. The full axiom of choice is generally considered to be non-constructive, but there are weaker versions of it, like countable choice and dependent choice, that are very commonly accepted within constructive mathematics.
And it's really interesting that even giving up something like countable choice can actually force us to rethink classical theorems in really insightful new ways.
Absolutely. Like, for example, Fred Richman's work on the fundamental theorem of algebra. So, constructively, you can't always pinpoint the individual roots of a polynomial. So, what Richman focuses on is approximating the multiset of roots, which is much more amenable to constructive techniques.
So it's not even necessarily about just limitations. It's about finding creative new solutions and new perspectives on these familiar problems.
Exactly. It really pushes you to think outside of the classical box and come up with new approaches that you might not have considered otherwise.
Now let's talk about how constructive mathematics tackles another big one, the continuum hypothesis. This is a statement that's famously independent of classical set theory, meaning that you can't prove or disprove it from the usual axioms. So how does constructive mathematics approach this?
Well, even the continuum hypothesis gets a makeover in constructive mathematics. It's reformulated in terms of detachable subsets of the natural numbers. So these are sets where, for any given number, you can definitively determine whether or not it's in the set.
So you're bringing it down to earth a little bit, making it more concrete
Exactly.
and computationally tractable.
It's trying to bring it more in line with the constructive spirit, but spoiler alert, even this constructive version of the continuum hypothesis leads to trouble, because it turns out that it implies the law of excluded middle in most settings, which is something that we generally try to avoid in constructive mathematics.
It's like we can't escape these fundamental logical questions, even when we're approaching things from a completely different angle.
It speaks to the complexity and interconnectedness of these foundational issues, that even when you change the rules of the game a little bit, some of these fundamental tensions still remain. And speaking of interconnectedness, that brings us to something that I think you as a philosopher will find very interesting, which is constructive reverse mathematics.
Constructive reverse mathematics.
Yeah.
That sounds really interesting. Tell me more.
So instructive reverse mathematics, or CRM as it's often called, it's really about trying to classify theorems not just by what they cut, but by the logical strength that's needed to prove them. So it's kind of like creating a map of mathematical dependencies. It reveals hidden connections between different areas of math that on the surface might seem totally different.
Oh, I love that.
It's like a philosophical treasure map for a mathematician.
It's about understanding the underlying structure, the connections
Exactly.
between these seemingly different concepts. I can definitely see why you as a philosopher would find this so appealing. So how does this actually work in practice?
Okay, so let's take an example, the fan theorem, which is a key principle in Browerian intermissionism. And it's all about finding this point of no escape within a branching structure. So imagine you have like an old-fashioned folding fan with these spokes, and imagine that there are infinitely many spokes. And the fan theorem says that if every infinite path along those spokes is blocked by a bar, then there has to be a finite point where all the paths are blocked.
Okay, I can kind of picture that. But how does this idea of fans and bars connect to other areas of math?
That's where things get really interesting. So the fan theorem in its various forms turns out to be equivalent to certain statements about how smooth functions are. It relates to this concept called uniform continuity.
Wait, so uniform continuity, which is all about how small changes in the input of a function lead to small changes in the output. That's somehow connected to fans and bars.
It's pretty amazing, right? So for example, one version of the fan theorem, called FT for detachable bars, is actually equivalent to something called the positivity principle, or POS.
POS.
Yeah, so POS basically says that if you have a uniformly continuous function on the closed interval from 0 to 1, and that function is always positive, meaning it's always above 0, then it can't get infinitely close to 0 without actually hitting it.
So there's like a safety net there.
Exactly.
That's preventing the function from completely vanishing.
Right.
So this very abstract principle about fans
Yeah.
is telling us something concrete about how functions behave.
It is, and that's one of the really amazing things that CRM reveals, these seemingly unconnected concepts, one topological, the other one from analysis, turn out to be intertwined at this very fundamental logical level. They have the same proof theoretic strength, meaning you need the same logical firepower to prove either one.
It's like you're discovering this secret passageway, connecting different wings of a vast mathematical mansion. And this kind of thing is happening all over the place in constructive reverse mathematics.
It's happening everywhere. It's a relatively new field, so there's still a lot of open questions, for example. We're still trying to figure out exactly which version of the fan theorem is equivalent to the full uniform continuity theorem for functions on the closed interval from 0 to 1.
So there are still pieces of the puzzle missing.
There are definitely missing pieces. We know that the uniform continuity theorem implies a version of the fan theorem called FTC for C-bars, but we don't know if the reverse is true. And we also know that a stronger version of the fan theorem called FT implies the uniform continuity theorem, but again, we don't know if the converse holds.
We have some of the connections, but the full picture is still emerging.
It's like we're pioneers charting a new mathematical landscape, and we're using logic as our compass and intuition as our guide.
But before we get too lost in these abstract landscapes, let's bring this back to our philosopher listener. What does all of this mean for someone who's grappling with these big questions of truth, existence, the nature of mathematical objects?
That's a great question. I think constructive mathematics, and especially CRM, offers a really fresh perspective on these age-old philosophical debates. It really challenges the traditional Platonic view that mathematical objects exist out there in some eternal realm, independent of us.
Right, Plato imagined these perfect forms,
Exactly.
and we're just trying to grasp at their shadows. But constructive mathematics suggests a very different picture.
It really does. It pushing us towards a more grounded view, maybe even a constructivist view, where mathematical objects are understood as mental constructions, or at least entities whose existence is tied to our ability to construct them, to compute with them, to interact with them in concrete ways.
So instead of these perfect ethereal forms, mathematics becomes something that we actively create and engage with.
Precisely.
And that has profound implications for how we think about mathematical truth.
It really does. I mean, if we can't point to a mathematical object, if we can't construct it or compute with it, then its existence and the truth of statements about it become much more nuanced, much more intertwined with our own abilities and limitations.
So it's almost like saying that the meaning of a mathematical statement is tied to our ability to cash it out, to demonstrate its truth in this tangible, constructive way.
Exactly. It's about grounding mathematical truth in our experience, in our capacity to manipulate and interact with mathematical objects. It brings mathematics down to earth, in a sense, and connects it much more closely to our computational and cognitive capabilities.
And that really resonates with a lot of philosophical ideas about the nature of knowledge and how we come to know things. It's like saying that to truly understand something, we need to be able to actively engage with it, not just passively contemplate it.
You're absolutely right. And I think that connection between mathematics and computation is really strengthened by the fact that, in principle, every constructive proof can be translated into an algorithm, into a computer program.
So it's not just about theoretical possibility, it's about this practical computability, which I think makes constructive mathematics all the more relevant. In today's world where computers play such a central role in our lives,
Absolutely.
so many reasons why constructive mathematics is so fascinating.
To mathematicians, philosophers, computer scientists, yeah.
It really is this rich and challenging landscape for exploration that pushes the boundaries of our understanding of what math is and how we know what we know.
It's a journey that takes you from the very concrete world of algorithms and computations to the very abstract realms of logic and philosophy, and reveals these surprising connections that bind them all together.
It really is a beautiful example of how different disciplines can illuminate and enrich each other.
I completely agree.
Now, you've talked about how constructive mathematics really requires us to be able to construct the objects that we're talking about. But doesn't that in some sense limit what we can explore mathematically?
I think that's a very common concern, and it's definitely a really important question. So on the surface, it might seem like demanding constructibility would restrict what we can do, but I think in many ways it actually leads to a much deeper and more nuanced understanding of the concepts involved.
Can you give me an example? I'm thinking about something like the intermediate value theorem. Classically, it says that if you have a continuous function on a closed interval, and the function takes on opposite signs at the endpoints, then it must have a zero somewhere in between.
That's a perfect example. So the classical intermediate value theorem, as you've stated it, is not actually constructively provable. because it just asserts the existence of that zero without giving you any way to find it.
Okay.
But there are constructive versions of the theorem.
So how do we make the intermediate value theorem constructive?
Well, one way is to add an extra condition. So if we require the function to be locally non-zero, meaning that it doesn't just touch zero at a point, but it actually crosses it, then we can constructively find that zero. We can actually devise an algorithm to locate it.
So we've made it more computationally tractable.
Exactly.
We've gone from theoretical possibility to actionable recipe.
Exactly. Just like with the Goldbach conjecture.
Exactly.
And it's not always about weakening theorems to make them constructive. Sometimes requiring constructibility forces you to rethink your entire approach. And this can actually lead to new and surprisingly insightful proofs. It's like constructive mathematics is asking us to be more creative, to find new paths to mathematical truth.
It's not a limitation. It's like an invitation to think differently, to approach problems from a new angle.
Precisely, it encourages this creativity and I think a deeper engagement with the mathematical concepts. It's like the difference between knowing that a path exists and actually walking that path. You experience all of the twists and turns, and I think you gain a much richer understanding of the terrain that way.
Yeah, it really does feel like a more hands-on, experiential approach to mathematics.
Yeah, and I think especially for a philosopher like you, it raises all sorts of fascinating questions about mathematical existence itself. What does it even mean for a mathematical object to exist if we can't construct it in some way? Does it have the same ontological status as something that we can manipulate and, compute with?
Oh yeah, we could go down that rabbit hole for a long time. But I think we should probably start wrapping up this deep dive. So for our philosopher listener out there, what's the key takeaway you want to leave them with? What's the one thought you hope they'll ponder as they continue their own exploration of constructive mathematics?
I think the most important thing to remember is that constructive mathematics, it's not just about swapping out classical logic for intuitionistic logic. It's really about a fundamental shift in perspective, a different way of approaching the very essence of mathematics. It's about grounding our understanding of mathematical truth in our ability to construct, compute, and interact with mathematical objects. And it's a journey that really challenges our assumptions, and I think ultimately rewards our curiosity. It leads to a deeper, and dare I say, more meaningful appreciation of the beauty and power of mathematics.
I love that. That's a beautiful way to put it. Well, thank you so much for guiding us through this world. And to you, our listener, thank you so much for joining us on this deep dive. Until next time, keep exploring, keep questioning, and keep constructing your own mathematical universe.